So for the story of Chapter 4, we're going to come back to one of the big overriding examples of the semester, and that is topography, elevation. And you can see Walla Walla has a lot of nice hills to illustrate these kinds of ideas. With partial derivatives, what we're really going to be able to do, at least in the context of topography, is to measure the rate of change of elevation in particular directions, really in the x direction and the y direction. And what's remarkable about partial derivatives is that's all you need. If you know the partial derivative in the x direction and the partial derivative in the y direction, you can figure out the rate of change in any other direction of the surface. So even though they're called partial derivatives, the two partial derivatives together, at least in the context of topography, gives you all of the information that you need to understand the rate of change of elevation at any particular location. So now I'm at the top of Scenic Loop Road, and something special happens to partial derivatives when you're at places like this. Here, let's set an x and a y axis here for a minute. So I'm going to draw an x axis and a y axis. So we'll make that the y axis. There's the x axis. All right, now as we approach the top of this hill, along the y-axis, you've got a positive partial derivative, right? The elevation is increasing as I go that way. And then in this direction, it's arguable that the partial derivative with respect to x is close to 0. We don't see much increase or decrease in this direction. Now, if I get right to the peak of the hill up there, what's going to happen is that partial derivative in the y direction is also going to be 0, and that point at the top is actually characterized by partial derivatives 0 in both the x and the y direction. It's what we would call a critical point. Now, a lot of what we're doing in this chapter is taking derivatives and finding extreme points. And this is a candidate for an extreme point because the partial derivatives are both 0 at the peak of this road. But it turns out it's not actually an extreme point. It's what we call a saddle point. Even though the partial derivative levels, or the surface levels off in this direction and levels off in this direction, we can see over that way it's higher, and over that way it's higher. That way lower, over the hill lower. This is what we call a saddle point, and you can imagine if you've ever seen the saddle on a horse, that's exactly what it looks like. We're usually not too interested in saddle points. We're interested in maximums and minimums. And so somewhere up here, let me turn the camera a little bit. Somewhere up that hill there's actually a maximum. There's a place where the partial derivative is in the x direction and the y direction are both 0, and in fact it's the peak of the hill. And you can see that in other places too, like that hill way out there. Maybe just right up that hill there. I don't know if you can see over my shoulder, but way off there in the distance there's a tractor tilling the field. That tractor is currently kind of heading up the hill in kind of the steeper direction of the hill, and it just finished kind of going across the hill, the shallower section of the hill. Notice that the steepness that the tractor experiences depends on the direction in which the tractor is traveling. That's a really important idea to understand, and we're going to see that idea when we study the directional derivative. I don't remember what section, but what we're going to see is, in the context of topography, the directional derivative tells us the rate of change at which the elevation is increasing or decreasing depending on the direction in which I point. You can kind of see that here. I'm standing on the hill here of Scenic Loop Road, and if I travel this direction across the road, I'm not really going up or downhill, I'm just kind of staying level. If I go this direction back towards my car, I'm going uphill, steep, and if I go this direction down the hill, I'm going downhill. The rate of change of elevation is negative. Here, the rate of change of elevation is probably 0, and in this direction, the rate of change of elevation is positive. So, unlike regular Calc 1, I guess, where there are really only 2 directions to choose from, you can go in the negative x direction or the positive x direction. Here, you have a whole lot of directions in which you can go. So you can have a curve in Calc 1 that's decreasing if I go to the left, increasing if I go to the right, and so on. But on a surface like elevation, you've got lots of different directions.